isomorphism game and quantum isomorphism and how it relates to hyperlinear groups, which is interesting because I don't know anything about hyperlinear groups. So maybe I'll need some audience participation for part of the talk. I did Google the definition this morning, so I wrote it down. So yeah. And I guess someone earlier in the week said that we want to avoid seminar talks, sort of like this traditional. So I've avoided the traditional step of preparing hardly at all. So I don't. It's going to be kind of winging it a little bit. Okay, but I'm going to start with this isomorphism game, which I guess I don't know. Not everyone was here last week, but some people were. But probably a lot of you have seen this isomorphism game. Well, maybe I should say what an isomorphism of graphs are first, right? So if I have two graphs, two graphs. No, come on. There's got to be some better chalk than this with this squeaky.
You should hold it on a different angle.
Yeah. If I put the board wrong. Right. All right. Which angle should I hold it at? Okay, maybe if I hold it orthogonal, it's a little bit better. But
like this.
Like this.
Yes.
All right, I can't do it. I can't write like that. I'm not gonna do that. All right. So if I have two graphs. That's right. Oh, I could just not write anything. Yeah, that'd be good. Okay. Right. All right. Okay. So I have two graphs, G and H, right? So I assume everyone knows what a graph is. And then, okay, what's an isomorphism, right? An isomorphism is just some bijection between the vertex sets. Such that if I have two vertices U and V that are adjacent, right? This means adjacent. Well, this is if and only if the images are adjacent, right? So probably everyone knows this, right? I mean, okay, it just means that the graphs are the same up to relabeling the vertices, of course, right? It's the sort of exact notion you would think of being sort of the same for two graphs. But I want to think about this in terms of a non-local game, okay? See, I already have to move it. I don't want to be crouching the whole time. So here we have our verifier V, we have Alice, and we have Bob, okay? And so in this game, what's going to happen is that, okay, there's kind of two versions of the game. One's slightly more complicated than the other version, right? We're going to do this simpler version, right, where we assume that the graphs have the same number of vertices, okay? So the verifier is going to send a vertex of, let's say, the graph G to Alice. We'll call it little g sub A. Okay? And then similarly, it's going to send a vertex of the other graph, sorry, of G to Bob, G sub B. Okay, and then Alice has to respond with a vertex from H. Where's some? See, this is a different kind of chalk because it's thicker. So maybe this one is better. It's only this much. Okay. So yeah, so they both get vertices from G and they have to respond with vertices from H. Okay. And the condition on them winning is that the relationship between the vertices from G should be the same as the relationship between the vertices of H. Okay, and by relationship, I mean, are the vertices equal, or are they adjacent, or are they distinct and non-adjacent? Okay. If you also allow loops on your graph, then you would need to preserve the property of having a loop. Also, actually later in the talk, I will probably use like vertex-colored graphs. So I can imagine that I have some colors on my vertices, and I require that I map red vertex, like I respond with a red vertex of H if I'm given a red vertex of G. Okay. Okay, and if I want to get really fancy, I could like color the edges or something like this as well. But so this would just encode also the color of the edge as well. But that's not as important for us. Okay, so that's the game, right? Of course, they can't communicate during the game, so they don't know what the other person's vertex they received is. But they can agree on the strategy before. And of course, the theorem is that, okay, I guess I should have introduced this notation before, but the two graphs are isomorphic, which I denote like this. That's if and only if classical players can win the game perfectly. I'll just say can win. Right? Whenever I talk about winning, I always mean winning perfectly anyways. Okay? I mean, if they're isomorphic, it's not so hard. You just say, pick your isomorphism between G and H, right? And whenever you get a vertex from G, you apply your isomorphism, you respond with that vertex of H. Okay. And then the other direction, again, is somehow not very difficult because you can, since you're doing it perfectly, you just, you can assume that they have some deterministic strategy, right? Because some probabilistic strategy, this is just like sort of randomly picking a deterministic one, right? And if you win perfectly, then you have to have that all those deterministic strategies win perfectly. And in a deterministic strategy, you just have a function from inputs to outputs, right? So exactly a function from the vertices of G to the vertices of H, right? And then the conditions of the game tell you that this has to be an isomorphism, okay? Maybe one thing I want to point out is that this is what's known as a bisynchronous game. Okay, so a synchronous game, this is just a game where the input set for both players is the same and the output set for both players is the same. And if the players get the same input, they must respond with the same output. So kind of like there's this consistency between the players. You can also think of this as kind of like a function game, right? Sort of like if you have one input for a function, you only get one output, right? You have this this vertical line test, right? This pencil test, like from grade school, right, or whatever, where you like hold your pencil vertically and you have like some plot of some curve, and you want to see if it's a function, right? And if the pencil only ever intersects at one point, then it's a function, right? All right. So yeah, so these synchronous games are kind of mimicking the property of being a function. Bisynchronous just means that if you get different inputs, you have to respond with different outputs as well. So okay, this is kind of like injectivity. Okay, and in this particular case,
The version of the game is actually not synchronous, right?
yeah, it's just synchronous. If I get the same input, I have to give the same output. Both versions of the game.
G is not necessarily in G. GA is not necessarily a vertex of G.
Yeah. G is, these are both from big G. This version, I assume they have the same size, and they always get vertices from G.
Yeah, but now they don't have the same input and output set, or do you just take the different?
No, they have the same input set. It's vertices of G. The same output set, vertices of H.
It's not the input set, it's the output set.
No, you don't need the input set to be output set, even for bisynchronous. Yeah. You don't even, I mean, in the general definition, you don't even need the output set to be the same size as the input set for bisynchronous, although I think all the work is done in that case. Right? That's sort of the interesting case. Yeah, so I mean, as I mentioned, there's another version of the game where you don't have to put this condition on the sizes of the graphs. The reason that you need it here is because if I didn't have this condition, I could have an isomorphism to a subgraph of H, right? And then I could win the game just as well, classically. But if you don't like that sort of arbitrarily imposing that condition on your graphs, right, then you can just make the game slightly more complicated where you can actually get vertices of either graph as inputs. You have to then respond with a vertex from the other graph, the graph that you didn't get a vertex from, right? And that means that Alice now either gets or sends back a vertex of G, and either sends back or gets a vertex of H, right? So in either case, there's still a G sub A and an H sub A, right? And then you still have the same condition. Right? And in that case, you don't need this assumption at all. It gets implied by the conditions of the game. Right. Okay. So bisynchronous. There's win. This. Right. Okay. Maybe I should very briefly. Okay. So now of course, since this holds, right, then that allows us to define the notion of quantum isomorphism, right, as being that the quantum players win. So we say G is quantum isomorphic to H, right, if quantum players can win. Okay, and actually I need to be a little bit careful here because there's like a bunch of different types of quantum players, right? Okay, because there's all these different correlation sets, right? So this is this Q set. So this means that they're using this tensor product framework for measuring on a shared state, right? So that means that they have some shared state which lives in some tensor product space, right? Everything for this, everything's finite dimensional. So they have some tensor product of finite dimensional spaces like Cn tensor Cm. Okay, and then Alice has her measurement operators, which are operators on Cn, and Bob has his measurement operators, which are operators on Cm, right? And then you take whenever you write down the correlation, right? So you get anytime you play the game, right? You're going to get some correlation, which is just these are the probabilities that, assuming Alice and Bob got inputs G sub A and G sub B, what's the probability that they output H sub A and H sub B, right? Okay, and for this these Q correlations, right? It looks like, so you have your shared state psi, and then you have, let's call it E, G, A, H, A, tensor F, G, B, H, B, and then psi. All right, and if I fix G sub A, right, and I vary over H sub A, this should be a measurement for Alice, and similarly for Bob, right? So these are all positive semi-definite, and they sum to identity for a fixed G sub A. Okay, so this is what it looks like in this Q strategy. And then there's also, I guess, QS. This is where I also allow, it's the same, but I allow infinite dimensions. Actually, in this game, it doesn't make any difference. Okay. In general, for correlations, it can be different. So the set of QS correlations is different from the set of Q correlations. But in all the synchronous games, I should say for synchronous games, there's a perfect strategy in one, if and only if there's a perfect strategy in the other. Okay? So you don't need infinite dimensions to do anything. I wouldn't say it's like easy, but I guess, I mean, this is some result of Vern's actually, right? It's kind of hinted at in a paper on these linear system games, okay, I guess the idea is essentially like, if you have this perfect strategy in this QS setting, then somehow it should break down as kind of like some block diagonal type thing. And each block actually should give you a strategy, which is finite. I think that's the rough idea. I think that's the rough idea.
Infinite blocks. So it's something that's in the appears to be an enclosure of the complex set, but it's something that can be written as a power series of things that are in the set. There's a beautiful theorem that you have in finite dimensions if you have a convex set, and you look at its summable closure in that sense. That's still the same set. So anything you can express as a power series stays in the convex set, even if the convex set's not closed.
Yeah. All right, yeah. So for all the games, I think that probably we'll talk about this entire event, I guess it will be the QS and the Q strategies will be the same, right? At least for the perfect ones. Then there's also QA, right? So for QA, this is like the closure of the set of quantum correlations. Right? So that, in terms of the game, it means that I can find a Q strategy. I can find a bunch of Q strategies that get arbitrarily close to winning perfectly. Okay. So maybe I can't find a Q strategy that sort of wins perfectly on the nose, right? But I can get arbitrarily close, so I can get sort of winning probability 1 minus epsilon for any epsilon. And then there's the last one is QC, right? And QC is where you don't have tensor product. You have the normal product, but you require that all of Alice's operators commute with all of Bob's operators, right? And of course, in this case now, the sort of the space of the shared state is just a single Hilbert space, right? But it can be infinite dimensional, right? Yeah, and then you just have that. So Alice kind of has, I guess, like sort of some subalgebra, and Bob has like a commuting subalgebra in a certain sense, right? In that case, actually, well, if you only use finite dimensional things, then it's the same. Okay? So if you restrict the finite dimensional operators, then the tensor product and the commuting setting, computing operator setting are the same. Okay. So if you want to really get a separation, you're going to need something infinite dimensional there.
That's true for all non-local games, right?
Yeah, I think that's true. I think that's true in general. I think you can somehow like just convert this to a tensor product formalism for an arbitrary sort of collection of measurements. Okay. Now, in these synchronous games, in particular in the isomorphism game, it turns out that, okay, these perfect strategies have to have some very nice form, right? In particular, all of the, well, up to some minimal sort of hand-wavy stuff, these have to all be projections. And Bob's operators have to all be projections. In the Q case, actually, they're just the transpose of Alice's projections, okay, and something more complicated going on in the QC case that I never quite remember. But somehow, in the end, what happens is that everything really boils down to just one set of operators, okay? And what this allows you to do, one set for, it basically allows you to just restrict to looking at Alice's operators in a certain sense, right? So well, this is for any synchronous game, actually. That's for any synchronous game. Okay.
Not completely trivial, right?
I wouldn't say it's trivial, right? It's, but I mean, it's at this point well known, I guess I would say. Yeah, yeah. Okay. Yeah, I mean, yeah, yeah. I mean, I think like in the tensor product framework, in the Q framework, right? I mean, it's maybe not explicitly written, but I think it's somehow known at least from this sort of quantum chromatic numbers paper. Right? I mean, they don't say this exact thing, but they definitely show it for this coloring game, right? So, and I mean, somehow like the condition they use is this consistency condition, right? So I think, and then Verne and others, maybe Yvonne was also, yeah, Yvonne proved it in this more general synchronous setting, right? Also for the QC case, and also like QA and all these things. Okay, but the main thing that I want to point out is that, okay, this allows you, since you can essentially only look at Alice's operators, this allows you to get a really nice formulation of this quantum isomorphism in terms of something called a quantum permutation matrix, which I guess probably a lot of you have seen. So I'll say, okay. Should say that J. Okay, so I have some matrix, right? Some capital P. The entries are these little Pij's. I and J run from 1 to n, let's say. Okay, and they need to be elements in some C-star algebra. Okay. And it's a quantum permutation matrix if the following holds. So the first thing is that all the entries are orthogonal projections. And then you have that if I sum any row or column of the matrix, I should get identity. So. Actually, if you assume this is equivalent to the matrix being unitary. So these are also called magic unitaries. Actually, in the quantum group literature, they're called quantum magic unitaries. Well, some people call them quantum permutation matrices now. Right. Okay, so this is a quantum permutation matrix. Of course, if this C-star algebra is just the complex numbers, right, then this just means that all the entries are 0 or 1. Right? And this means that there's exactly 1, 1 in every row and column. So it's a permutation matrix. Right? Okay, and then it turns out that G and H are QC isomorphic. So they're quantum isomorphic in this quantum commuting framework. Right? That's if and only if there exists Q perm matrix P such that if I take the adjacency matrix, or the adjacency matrix of G times P, this should be equal to P times the adjacency matrix of H. Okay.
You need a trace.
I mean, of course, I do need a trace, right? But then I don't need it.
It's something well behind it that you can get rid of the trace.
Yeah, so we'll get to it, but basically the quantum automorphism group allows you to get rid of the trace. So I will talk. You can steal the Haar state, which is a tracial state, from the quantum automorphism group of the disjoint union. Yeah, that's exactly what happens. So you retake the. Yeah, I'll get to it in a few minutes. Okay, so I mean, this is just really nice because it's exactly sort of the analog of the kind of algebraic, I guess, definition of isomorphism in the classical case, right? If I had this for a permutation matrix in the graphs, that's if and only if the graphs are isomorphic, right? It's usually written as P transpose A sub G, P A sub H, right? But okay, I can just move the P over if I like, and maybe this is a little bit more palatable because I'm taking like, you know, a scalar matrix times a matrix with some weird C-star algebra entries, right? Well, not weird for most of the people here, I guess. Pretty normal for you. Weird for us, yeah. For us. Right? And now I have the same thing over here. If I have the P transpose here, right, then I have, actually on the right, I actually have some matrix which has C-star algebra entries, and on the left, or on the right, I have scalar entries, right? So actually I would need to tensor this with like the identity from the C-star algebra, right? Although some people just leave that off, I think.
For like if there's any people who like to think about quantum information, is that this quantum permutation, once you put the C-star algebra inside some B of H, all the rows are going to be like PDNs and all the columns are going to be PDNs.
Yeah, I mean, okay, I mean, if you think of these as sort of some operators on a Hilbert space, right, then this is exactly saying that, okay, all the columns and all the rows are a projective measurement. That's exactly right. Yeah. Okay, and of course they correspond exactly to, say, Alice's measurement operators, if you like. Okay? Which is why I was saying this thing about like, okay, somehow like we can only look at Alice's operators. So this is essentially what I meant. Okay?
But somehow for the non-local games interpretation, you only need either rows or columns to be PDNs.
Yeah, of course, if I had a synchronous game, right? Well, of course, I won't be able to do this for a arbitrary synchronous game, right? But I would have something where, like, say, all the rows are projective measurements, right? But the columns are not necessarily, right? Yeah.
So in this you don't fix the C-star algebra. So
I allow any C-star algebra here. Yeah. So I probably should have stated it as I need the entries of this to be in a C-star algebra that has a tracial state on it. Okay. So that kind of follows from results of Verne and Ivan, right? So that holds for kind of like any synchronous game, right? You can show that, okay, there's this perfect QC strategy for a synchronous game if and only if you have this collection of projections that has all the right orthogonalities living in some C-star algebra that has a tracial state, right? I don't know, Vern. Is this just the purification of the tracial state? I mean, this is, it is true.
It is already tracial. It is, psi will be already, if this is a synchronous thing, psi will already be tracial.
I guess if you start from the other side.
Yeah, but if you start from, if you start from the tracial state, right? Yeah.
Yeah, but somehow. Somehow quantum mechanically, the way that the strategy is defined is that it has this nice mathematical characterization that you can just think about traces because it has been shown that.
Someone has the fancy chalk over on this table.
What is the fancy term?
This Hagoromo, the Japanese one, yeah. So. No, I mean that you will need to use the synchronicity of the game, so this kind of consistency type condition, right? And I think what you can show is like, if I act with this on psi, it's the same as acting with sort of e sub the same thing on psi, and then okay, then you do a bunch more stuff, but that's sort of how you show that it's this tracial thing. Okay, yeah. So I didn't get to all the lectures from last week. So.
Two of the sentences prove really once you have the kind of gadget of kind of states. Pretty density satisfy the sequence. The sequence allows you to throw one to the other.
Yeah. You can replace all the f's by e's when you're acting on the state. And that's like some Cauchy-Schwarz proof, right? You do Cauchy-Schwarz like 2 or 3 times.
The Cauchy-Schwarz inequality.
Yeah.
It's kind of very simple. I mean, I think nowadays kind of have a very kind of short proof of that.
Yeah.
And at any time the density satisfies this bisynchrony condition, be a trace sum.
It's bisynchronous between input and output sets of the same size.
Yeah, but if you start now from the right-hand side, just see algebra, you say, does it have a trace a priori?
I mean, we will see that we can get away in this case with not having a trace, but for a general synchronous game, you need the trace. Well, I don't know if that's a theorem, but in general, the result is for synchronous games is that there's a trace there.
What within the side, if you just start
If you start with some arbitrary trace, I mean, I don't know. That's GNS. Oh, without a trace. Oh, in this case, in the case where you are really in the isomorphism game case, because for synchronous games you need the trace. For if it's not isomorphism game.
If you have this a very strong condition, so pick up any state on this over space, it will give a specific realization.
Will it then turn out to be the trace?
Not necessarily, right? It will give you a correlation. Then from this you can claim that there is another one that will give you the same thing, basically a trace.
I think you need to pass to another C-star algebra.
Another representation. The C-star algebra doesn't see what it is on the presentation. But yet, right isn't the correct trace. Like quantum
If it is such a quantum permutation matrix, then you know that it's universal C-star algebra for this game is non-trivial, and that one has a trace, but like the one you started with.
If you want to know how you get the trace in the isomorphism case, I will explain that in a minute. I will give a vague explanation of it. I will give some explanation.
Yeah, in general, you just need to request that there is this trace.
Yeah, if it's not the isomorphism game, if it's just a synchronous game, then you will need to require that there's a trace. Like to get the if and only if, I mean, it won't be exactly like this, but it will be if and only if there's some projections in the C-star algebra that has a trace, right? But if you drop that has a trace condition, there's no if and only if anymore.
Even for bisynchronous.
Well, for
general.
yeah, for general bisynchronous, if it's not between sets of the same size, then you can't do it. Maybe I don't know about if it says sets. Anyways, we'll get to it. Okay. All right, and okay, I should also say what happens for the other Q's. All right. So for if it's just Q here, right? Now I do need to restrict that this C star algebra is like finite dimensional, some like Mn of C for some n, right? Okay, so I need that these things are actually kind of matrices. Okay, so that's what you get for Q, right? And then for QA, so this is the one I'm least familiar with. It used to be that you always use this amenable trace phrasing. Now it's all something about some ultra filter, something. I don't know anything about that, right? So I think what happens for the QA case is that you have this, but now you need to require that the C star algebra you're using has an amenable trace. Is that correct? Perfect, right? Okay.
Or alternatively, the PIJs all come from R omega.
Yeah, or alternatively, all the PIJs come from R omega, whatever that is. Right? Okay. Right. So that's what happens. So I mean, yeah. So if you put some, if you want to look at this sort of more restrictive quantum type isomorphisms, you do need to put some extra conditions here, right? So they're not all equivalent. Well, okay. Actually, we don't know if QA and QC are equivalent for isomorphism. We'll get to that actually. Okay. And maybe I'll quickly point out, maybe this was kind of implicit from what the discussion before, but like in the case where you have this tracial state on the C star algebra, right, then you can get sort of your correlation by just applying the tracial state to the product of these things, right? So, and that'll give you exactly your correlation, right? Okay, but this leads us to the quantum automorphism group, right? Because, I mean, if you knew about quantum automorphism groups and you saw this, then you would already sort of immediately jump to quantum automorphism groups. Of course, we didn't know what quantum automorphism groups were when we were doing this, right? And if you Google, right, and you're us, you Google quantum isomorphism, not quantum automorphism, right? And then you get a bunch of papers about quantum algorithms for graph isomorphism, right? So you don't find all the quantum group literature. So you have to kind of accidentally stumble upon it, which is what happened. Okay, okay. So for the quantum automorphism group, it's all right. So let's call it this of use this notation, right? So this is one of these compact matrix quantum groups, orthogonal compact matrix quantum groups even, right? Okay, which means it's defined in terms of this matrix of generators, right? So it you have, and it's exactly that you have this quantum permutation matrix, right? Maybe I should actually write that. Okay, so this C, right? I mean, this doesn't exist. This is not a real thing, right? Okay. Right. This is the universal C star algebra. Right. With generators. Let's call it U sub G prime, right? Such that this matrix of these generators is a quantum permutation matrix. And this A sub G times U equals U A sub G. Right? Okay, so it's like exactly this, except for that instead of G and H, I have G and G.
Okay, would it make sense if you just need to consider unit graphs here?
Maybe. Yeah, I don't know. I think it could be interesting. I mean, these non-local games, people don't usually look at games with infinite inputs and infinite outputs, and I don't know if there's a lot of results on that. But I think it could be interesting because it would be nice to have a notion of quantum isomorphism of infinite graphs also. Oh, there is one. Okay, then I should. Okay, but they don't do it in terms of a game, I assume.
Different information, but not really in terms of games.
And it's also a very restricted class of infinite graphs, right?
But you don't need that. I have this paper.
Yeah, that's also very interesting.
Okay. Yeah. Okay. Maybe I spoke in error.
Isomorphism.
Right.
And this kind of characterization of quantum isomorphism is equivalent to these kinds of very unitary. Yeah, that's kind of like the definition.
Yeah.
Yeah, but then yeah, I think there's not the game in that case.
No,
Or, yeah.
no, but you have like a pointed homomorphism comes from planar graphs as well, but not really. There is no game. Like all the other like formulations, like the other more algebraic ones are equivalent, but there is no
Okay.
game.
So there's probably like this theorem about like the orbits of the disjoint union or something that also holds, I guess, in the infinite case, if it's connected, I guess.
Technical challenges because the quantum automorphism group can be non-compact in that case, so it is locally compact or discrete.
Yeah, I guess there's also this notion. This is not an infinite graph, but it's you can look at these graphons, right? And I suppose you could also try to consider quantum isomorphism of graphons. I don't think there's a notion of that yet, right? Because there is a paper about fractional isomorphism of graphons, which is some other linear kind of relaxation of graph isomorphism, where instead of this, you have a doubly stochastic matrix here, and that gives you something called fractional isomorphism. Right? And apparently, there's a notion of this for these graphon things. Okay?
Yes, that's the NC class, the NC perfect subdivision.
The non-signaling. Oh, yeah. That's the non-signaling strategy. Exactly equivalent to having a non-signaling strategy. Yeah. But for that, you need a more complicated game. You really need it there. You can't get away with just assuming they have the same size. Doubly stochastic. If you replace it with doubly stochastic, that's known as fractional isomorphism. Huh? Yeah. So all the entries are non-negative, and they are all the row and column sums are 1. No, that's more relaxed than quantum.
It's not 0, 1 entries, right? It's all real entries.
I don't require that the entries are square to themselves, right? Right here. Yeah.
Positives that come to 1 along rows can't necessarily unitaries. It is strict relaxation.
Okay. Okay. Yeah. So all right. So we have this quantum automorphism group. And okay, you can see very clearly there's a connection here, right? But we would like to make it explicit, right? And for this, we need this notion of orbits of the quantum automorphism group, okay? So for that, we just say, okay, I'm going to define a relation. I'm going to define a relation, the tilde 1, right? And I say that G is sort of tilde 1 related to G prime if this U, G, G prime is not equal to 0, right? So this U, G, G prime not being equal to 0 is essentially saying that, okay, I will map G to G prime with some sort of like non-zero probability in a certain sense. That's not the right phrasing because it's not probabilities, but right. Well, yeah, I'm not even really talking about a strategy. I'm just talking in terms of the quantum automorphism group. It somehow means that okay, G can be partially mapped to G prime or something like that, right? I mean, in the classical case, it's exactly that there's an automorphism that maps G to G prime, right?
Yeah, but not every.
Sure, not every automorphism, of course, yeah, right? And so in the classical case, right, if there's an automorphism that maps G to G prime, this just is the definition of G and G prime being in the same orbit of the automorphism group, right? And so what you want to define is, you want to use this to define a notion of orbits of this quantum automorphism group, right? Which it turns out you can do, because actually this turns out to be an equivalence relation, okay? And so then you just define the orbits of your quantum automorphism group to be the equivalence classes. Okay? And then you get the following theorem, which is that so if G and H are connected, then G and H are QC isomorphic if and only if there's some vertex of G and a vertex of H in the same orbit of the disjoint union. Okay, so this is, again, exactly analogous to the classical case, right? Right? If I have two connected graphs, I can just take the disjoint union, right? And the graphs are isomorphic if and only if there's some vertex in G that can be mapped to a vertex in H, right? By an automorphism of the disjoint union, right? Because if I map one vertex from G to a vertex of H, actually I have to map all of G to H, right? Because they're connected, okay? And so then the exact same thing holds for the quantum case. And the connected, this is not really a restriction because, well, I can always assume G is connected by taking complements, right? Because taking complements doesn't change whether two graphs are quantum isomorphic, right? So I can assume one of them is connected. And then you can show that if I have a connected graph, it cannot be quantum isomorphic to a not connected graph, right? So that doesn't, this is no restriction. Okay? All right, so this is kind of like the explicit connection between the quantum isomorphism and the quantum automorphism group, I would say. Right? And this is also how you get rid of the trace. So what happens is that, okay, of course, just from, I mean, one direction is obvious. I mean, if I have this but with the tracial state, then I also have it without the tracial state, okay? Right? But if I have this without the tracial state, then when I look at this disjoint union, okay, I guess I should switch to the other board. Right. So suppose I had this right without the tracial state here, and I want to get the tracial state. Okay. So what I do is I look at this disjoint union, right, and I look at this quantum permutation matrix U, right? That is like this, they call it the fundamental representation of the quantum automorphism group, right? So this partitions, right, into this kind of block matrix, right, where this is G, G, H, H, right? Okay? And if I have this, right, then I can, okay, maybe I should, let's not look at the fundamental representation at first. Now let's just, I'm going to build a quantum permutation matrix that commutes with the adjacency matrix of the disjoint union. And the one I'm going to use is I'm going to put P here and P transpose here, right? And this P is from here, okay? And it's very easy to see if you just write out the equation, right? That this commutes with the adjacency matrix of the disjoint union, right? Because the adjacency matrix of the disjoint union just looks like A sub G, A sub H, and then 0 alpha. So if you just write out the block, like the equations for each block, it's exactly going to give you this thing that you already have. So you know that this commutes with the adjacency matrix of the disjoint union, right? And in this case, there's at least one non-zero entry here, right? Well, there's actually lots of non-zero entries, but there's at least one non-zero entry here, right? So since there's at least one non-zero entry here, right, that means that in this U from the quantum automorphism group, since it's the universal thing, right, there's an entry here which is non-zero, okay? Then the other thing you need to show, okay, is that in this U, everything here is orthogonal to everything here and here, okay? And this is just corresponding to the fact that H is connected. So when I take the product of something from here and here, it's going to look like U. So something from here looks like U, G, G prime. And then something from here looks like U, G prime, prime, H. Okay. And this is going to have to be 0 because essentially the idea is that, okay, these are both from G. So there's some path between them. Okay. But there's no path between these in this disjoint union. Okay. And so this product in that case has to be 0. I guess what you could show is that, okay, if I have a walk of length L between these two vertices, right, then if this is not 0, I have to have a walk of length L between these two vertices. Okay? So I don't want to go into the proof of that, but it's not something which is very hard to do. Okay? And so you get that this is 0, right, which means that everything here is orthogonal to everything here, and similarly to everything here in this fundamental representation. Which means that this, in the fundamental representation, is like a sub-quantum permutation matrix. And it's a non-zero one, right? Because we know there's at least one non-zero entry there. Okay. Right. And now what you do is you take the Haar state from the quantum automorphism group, which is tracial, and you just restrict it to the subalgebra generated by these entries. Okay. And that gives you, well, after you renormalize, it gives you a tracial state on those, right? And then you use that for your tracial state that you didn't have before. Okay. Yeah. I mean, that was a little bit hand wavy, I guess, but are there any questions about that? Maybe something was not clear. Okay. All right. Well, that's a rough idea. What time is it? 10:22. Okay. All right. Maybe I also want to say a little bit something about orbitals. Okay. I know I mentioned this definition of orbits. Okay. But I also want to talk about orbitals just because I think they're sort of nice to know. So I can define a relation on ordered pairs of vertices. So now let's go back to this quantum automorphism group of G, right? So I'm going to define, let's call it G1, G2, 2 related to G1 prime, G2 prime. If U, G1, G1 prime, U, G2, 2 prime is not equal to 0. Okay, so it's very similar to this relation I defined for the orbits. I probably should have mentioned that this definition of orbits goes back, I think, to Banneker or something. It's been known. But it's very similar, but now instead of just looking at a single generator, I look at a product of two generators. Again, in the classical case, what does this not being 0 mean? It means that there's some automorphism that maps G1 to G1 prime and also maps G2 to G2 prime. Okay? So if I think about orbits of the automorphism group on ordered pairs, right, it's saying that these two ordered pairs are in the same orbit. Okay? All right. And then, of course, you can show that this is also an equivalence relation for the quantum automorphism group. Okay? And so that means the notion of orbits on ordered pairs for the quantum automorphism group also makes sense. So you take those to be the equivalence classes of this equivalence relation. Right? And we often call these orbitals, just so we don't have to say orbits on ordered pairs all the time, right? Because often you're working with both orbits on vertices and orbits on ordered pairs, right? This comes from the classical literature. Right? So I will call them orbitals, right? But they're just orbits on ordered pairs. I mean, in the classical case, you can also consider orbits on arbitrarily linked tuples. Turns out that doesn't really work out for the quantum automorphism group. You can't define like a good notion of orbits on, say, 3 tuples or 4 tuples or whatever, okay? So that starts to break down.
Wouldn't AB equal to 0, BA not equal to 0, that kind of situation cannot occur, right?
You can't have that this is non-zero, but sort of when I swap the order. Because they're self-adjoint, yeah. All the entries are self-adjoint, right? So if I take star of this, then I get the. Okay.
Maybe it's important to note that you're not actually
you don't actually have an action of the quantum automorphism group on ordered pairs.
Sure.
There's no quantum permutation matrix unless you add additional relations to you.
Sure, but I didn't talk about actions at all, so but yeah, there's not an action on ordered pairs. You're exactly right. This is action on vertices, right? But there's no action on ordered pairs, right? In fact, I think you won't have an action on ordered pairs unless you would need to have that everything is commutative.
Now you need to add these relations that Duchamp has.
But that would only give you action on the edges, right? Yeah. So if I want on every ordered pair, I need that commutation relation for every pair, and then I just get that everything commutes. Yeah. Okay. So you get that you have this notion of orbitals, right? And it's also not hard to see. Well, okay, it's not completely trivial, but it's not very hard. That if I take an arbitrary matrix U, M, then it's going to commute with this fundamental representation U, right? If and only if, whenever I have some Mij not equal to MLK, this implies that U, I, L, U, J, K is 0. Okay?
So M is a scalar.
M is a scalar matrix, yeah. So I have some scalar matrix. It commutes with this fundamental representation. Oh, I guess this is actually something that's true for any quantum permutation matrix U. Okay? So it will commute with this quantum permutation matrix U if and only if, whenever you have sort of two different values of entries in M, right, then this corresponding product is 0. Because what is this saying? It's saying that, okay, if like, if I want to think of this as some sort of like kind of weighted adjacency matrix or something like this, right, this is saying, okay, I have some edge of weight, whatever this is, M sub ij between I and j, versus an edge of some different weight between L and K, right? So I should not be able to map I to L and j to K, right? I should not be able to map this ordered pair to this ordered pair, right, by a quantum permutation.
This is saying essentially that it has to be constant.
This is exactly saying that this has to be constant on the orbitals of the quantum automorphism group. Exactly. And so I mean, if you take the converse, yeah, I mean, yeah, exactly, right. Because if I take the contrapositive, right, it's saying that okay, if this is not 0, meaning that these things are in the same orbital, right, then I have to have that this is equal. Exactly. Okay. And from this, what you get is that these orbitals are rather what you get is if I look at say these matrices, like kind of the characteristic matrices of these orbitals, right? So I have a 1 in an entry where that ordered pair is in that orbital, right? Then these form something called a coherent algebra. Okay, so if I take some a sub, let's call it R. So if R is an orbital of the quantum automorphism group, okay, then I let this a sub, I should do superscript, I guess. So if I look at these matrices for all my orbitals R, these will form something called a coherent algebra. In fact, they span. Okay, and what this means is that it's an algebra, right, with the following conditions, right? So I need that the identity matrix and J are in it. Let's call it algebra A. Okay, but it's just a sub-algebra of the matrix algebra, right? Then I also need that, okay, if M is in, it needs to be self-adjoint. Okay. And then I also need that if I have two matrices in my algebra, then their entry-wise product is in the algebra. Okay? All right. So these orbitals of the quantum automorphism group form this coherent algebra thing, which on its own is maybe not super useful because you can't find these orbitals. It's undecidable to determine the orbitals. It's undecidable to determine the orbits, because if you can determine orbits, you can determine quantum isomorphism, and that's undecidable. Okay, but you can somehow approximate these orbitals of the quantum automorphism group, because you know that it's a coherent algebra that contains the adjacency matrix of your graph. Okay, so that means that it must contain the smallest coherent algebra that contains the adjacency matrix of your graph, and that you can find quickly. Okay.
So can we just, so putting together this condition at the bottom means, so is this algebra we get exactly the things that commute?
Exactly. It's exactly the things that commute with you. Right? It's the like you think it's the commutant somehow. Like, and in the classical case, it's also exactly the things that commute with every automorphism of the graph.
So once again, so just to make sure that they understand the word. So you have these ARs, right? You have a bunch of ARs. And then you say they span the coherent algebra. So you just take linear
Combinations, yeah.
combination.
Yeah.
And then they would be an algebra.
It will be an algebra, yeah.
So this can be additional three property.
Yeah.
Is it clear they would be an algebra if you just take a linear span?
It's because of this, right? Because this is where they come from, right? Because if I have two of them that commute with you, then their product commutes with you, right? So the products are contained in the linear span, right? So I mean, like, it's clear that the linear span of these things are exactly the things that commute with you, right? Yeah.
Are you thinking of these as ordinary numerical matrices?
Yeah, these M's are scalar matrices. These are scalar matrices, right? The only funny matrices are you.
The only thing which is slightly new and surprising is the last property.
Yeah, and this is not really. I mean, this is kind of like almost implicitly known, I think. I mean, Banneker, I think, knew that if I have I think I saw this in a paper by Banneker, maybe someone else. Like, oh, if this holds, right, then I can look at like pick a particular value, say 3, and I look at all the places where all the entries of M equal to 3, and then I just replace those with 1s and put a 0 everywhere else. Then that matrix will commute with you, right? And that's equivalent. That's equivalent to this. Okay. All right. Yeah, but I think there was no language. There wasn't the terminology for it in the quantum group community at the time, right? But this is something which is common in algebraic graph theory.
In the Isomorphism paper with give a different characterization of this algebra.
Okay.
We take the density, the density for the game, the P,
Mm-hmm.
and we use that to define a CP map by the
Yeah.
GAGB matrix units goes to the sum of the HAHB matrix units with those numbers in front for scaling. And that gives you a unital trace preserving map on M.
Yeah. This gives you the projection onto this coherent. Well, okay. I guess if you're going from one graph, to the other. Right. So the point I wanted to make is just that, okay, I can't find these quantum orbitals, right? That's undecidable, but I can find approximations to them because I can find the smallest coherent algebra that contains my adjacency matrix. Okay, that's doable in polynomial time, okay, by something called the Weisweiler-Lehmann algorithm.
Can you give some simple example where this can be computed?
I guess, I mean, I could do something like, a 5 cycle, right? That's very simple. The simplest example is if I take a complete graph or an empty graph, right? The complete graph or empty graph, right? Then this algebra is just going to be the span of I and J, right? Or I, so these orbital matrices will be I and J minus I. Okay. For the 5 cycle, right? I mean, I also, since I'm a graph theorist, right? I want to think of these matrices also as, I can think of them as directed graphs, if I like. Okay, so for the 5 cycle, I mean, you get one of these things which corresponds to all the edges, right? Which is just the adjacency matrix, right? And you also get the adjacency matrix of the complement. So that's like these another an isomorphic, right? Another 5 cycle, right? But the complementary one, right? And then you get the identity, right? The diagonal part. Right? Okay, I mean, you can do more complicated things, of course. And in fact, if you take a random graph, it's going to just be all the matrices. Asymptotically, almost surely, if I pick a graph on n vertices at random, then the smallest coherent algebra that contains the adjacency matrix is everything, right? Which is how you show that asymptotically, almost surely, the quantum monomorphism group is trivial. Right? It's just immediate after that. Right? Yeah, but you can sort of get this approximation to the quantum orbitals using this, right? In particular, what this is really telling you is giving you some orthogonality conditions on this fundamental representation that you didn't have before necessarily, right? Sort of to begin with, really all you had is that, okay, this product is 0 if somehow these were equal and these were not equal, or these were adjacent and these were not adjacent, or these were distinct non-adjacent and these were not distinct non-adjacent, right? Those were the orthogonalities you know sort of a priori, okay? But this is giving you some extra ones. So in particular, it means that the distance has to be preserved, right? So if I have if these are at a certain distance and these are at a different distance, then this must be 0 because these, this ordered pair and this ordered pair will be in a different part of this, it's called coherent configuration, just the sort of combinatorial counterpart of the coherent algebra. Right? So I mean, when I find the smallest coherent algebra that contains my adjacency matrix, right? And again, it's going to be spanned by some 0, 1 matrices because of this property, right? And those 0, 1 matrices are just, I can think of those as collections of ordered pairs, right? And if I have 2 vertices at different distances, then those ordered pairs are in different parts of that partition of all the ordered pairs. So, of course, for some graphs, it doesn't tell you anything new, right? If I have a strongly regular graph, actually, this coherent algebra is, again, just identity, the adjacency matrix, and the adjacency matrix of the complement, right? And then it tells me nothing new, right? So it's kind of useless in that scenario, right? But in other cases, it can be very useful, right? Okay, I guess. So okay, I guess the easiest thing to say is that if I look at the power of the adjacency matrix, right? Well, I mean, in this coherent algebra is an algebra, so I can take products, right? No, it's okay. These, I said it, but I didn't write it. I guess so. This is an algebra. I'm sorry. Yeah, that's my fault, right? Otherwise, like, I mean, if I can only take intro as product, and I would never get anything new, right? Yeah. So it's an algebra, meaning I can take products and linear combinations, right? Yeah.
You can explain a little bit of the Weisweiler so that where the colors come from, where the base is not similar.
You want me to explain the algorithm?
Would clarify something.
I mean, I guess okay, yeah. Okay, Peter wants me to explain this Weisweiler-Lehmann algorithm. Okay, about the distances, right? The entries of this count the number of walks of length L between 2 vertices, right? Okay, so if I have 2 vertices at distance, say L, and then 2 other vertices at distance K, where K is greater than L, then in this matrix, right, there will be a non-zero entry versus a zero entry. So already that would do it. Okay. Okay, Peter's requesting some explanation of this Weisfeld-Lehmann. I think then we should probably take a break because it's been an hour. So, I mean, what this is doing is that this is kind of like this is an algorithm that sort of starts with you've partitioned all the ordered pairs of vertices into three parts. Things that look like, things that correspond to a vertex in itself, right? And then things that correspond to ordered pairs that are adjacent, and things that correspond to ordered pairs that are distinct and non-adjacent, right? So sort of the initial like C0 of, let's call this ordered, like, okay, U comma V, right? This is, let's just say it's 0, 1, or 2, like if U equals V, U adjacent to V, U not equal to V, and U is adjacent to V, okay? And then what you do is you kind of refine this coloring iteratively, right? So you, for C sub I of UV, right? How do you want to write this, right? So first is you retain the information of the previous coloring, I guess. So you have C sub I. Maybe Peter's going to get mad at me because if I don't do it the way he wants me to do it. Okay. I don't have this. He's the expert actually on this. So, all right. So you retain the information of the previous coloring. But then what you do is, so let's look at this. So you have U and V, right? They don't have to be adjacent, right? But I can think of them as being sort of having a directed edge of this color, or sort of this color between them, let's say, right? So, and what I do now, right, is I look at vertices W, right? And I look at sort of the color of this UW ordered pair, and I look at the color of this WV ordered pair, right? Okay. And I kind of collect that information for all W, right? So this is going to be the multiset of ordered pairs of Ci minus 1 of UW, comma Ci minus 1 of WV, such that W is a vertex. Okay, so this is a multiset, right? The information of this multiset is just sort of counting the number of vertices W, right? Such that these two colors are some particular two colors. Okay, so it's sort of counting the number of different types of colors of triangles like this. Okay, and so you just do this refinement step until it stabilizes. Okay, and then this gives you your meaning that the partition that I get is the same at the next step. Well, it's the most quadratic, right? Because there's only quadratically many ordered pairs. Yeah. So yeah, at worst you have quadratically many steps, right? Actually, I think in practice, at least in the thing I read, that was like this book by Weisfeld-Lehmann, they actually do this by just doing matrix multiplication, right? So you make some matrix with some variable entries, right? And you multiply them, right? And then you just sort of look at the expressions for each entry, right? And if they're different, right, then now you kind of you get a new. This gives you the new partition, right? And now you take sort of this like arbitrary linear combination of the new 0, 1 matrices, right? Where you have variable coefficients in a certain sense, and you do it again, right? So it's actually just matrix multiplication, but some variable entries. Okay.
So I always describe this as an algorithm, like the operator algebras. I would describe this as an algorithm that computes the coherent algebra generated by the adjacency matrix. But David thinks that's funny because it actually uses the matrices to compute.
Yeah, because it's somehow like, okay, this is
Smallest.
Yeah, but the actual way they do it, at least in the original book, is that they do matrix multiplication, right? So somehow like I went from matrices to this combinatorial thing and said this combinatorial algorithm, but that's not how they actually do it. They do it with matrices, right? Okay. Anyway, so you can find it. So an intertwiner for the quantum automorphism group, well, an LK intertwiner, is a matrix which satisfies this equation. Okay, so T is a scalar matrix, right? And this tensor power, right? I mean, it's kind of the usual thing you would imagine, right? So if I look at, say, the I1, I2, dot, 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 IL, comma, J1, J2, dot, 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 JL entry of this thing, right? Well, it's the I1, J1 entry times the I2, J2 entry, so on. Okay? Of course, the order matters in that case because it's the entries are not necessarily commutative. Okay. So this is an LK intertwiner, right? I guess maybe the interesting thing is that, well, okay, these intertwiners, I mean, if you have two intertwiners of the same size, then you can take linear combinations, it's still an intertwiner. You can take tensor products and that of two intertwiners, that's an intertwiner. If you're able to multiply them, then you can multiply them, and that's an intertwiner, right? So they form some collection of matrices that's called, like, what's the name? It's a concrete something category duals or something like that. It's got some name. It's formed something, right? Okay. And what's, I guess, the interesting thing is, okay, this theorem by Varanovich is that, okay, these things, whatever they're called, are in sort of one-to-one correspondence with these complex matrix quantum groups. Okay. So somehow the intertwiner is actually containing all the information of the quantum automorphism group, the graph. Okay. And for the quantum automorphism group, these intertwiners are actually generated by just for all okay. For the quantum automorphism group, the intertwiners are generated by some small set of intertwiners, just three, which are well, okay. Actually, maybe I should. So if I take U times the R1's matrix, this is, sorry, the R1's vector, I should say, is equal to U times U tensor 0, which is just a 1-by-1 matrix with the identity from the C-star algebra in there. Okay. And then if I take, there's this matrix M, I guess I used M earlier, but this is a matrix which, when I multiply by EI tensor EJ, these are standard basis vectors, this is delta I J EI. This is exactly one of these spiders, the standard basis spider with 3 legs from Bob's talk yesterday. Okay. All right. And then the other intertwiner that you need is the adjacency matrix of your graph, right? Of course, that's an intertwiner by definition of the quantum automorphism group. These two being intertwiners is just definition of quantum permutation matrix. Okay.
Is M the co-multiplication?
No, M is this multiplication. The co-multiplication is like, I mean, this is just a scalar matrix. Okay? Co-multiplication is a homomorphism from this algebra to the tensor product of the algebra itself, right? Right. M is not that at all. Right? I mean, this is everything here is just scalar stuff. Okay?
If you think of, there's a coaction in the background of an Newton C-star algebra. This is the multiplication.
Okay, but yeah, if you for the quantum, if you write down sort of what these conditions mean, this exactly gives you the conditions for it being a quantum permutation matrix. Okay, just if you just write down like entry-wise what these equations mean. Okay, so not really anything deep there. Okay. The T's are scalars. Yeah, these are always some scalars. Not the only weird matrices here are U's. Okay.
But in this case, I guess from k-fold tensor product of the n-fold tensor product.
Yeah. CN, yes, CN. Yeah. Yes.
These two intertwiners that we do, they probably came up in, was it Mike's talk with that picture?
So I will show the pictures now, right? The pictures look like this.
So there where you don't write anything, there's just one, right?
Where's one? What?
Yeah, one, at least one there.
Yeah, yeah, as usual. Right? Okay. I mean, in fact, also this is a spider, but with just one leg. Right? Okay. I guess he was doing everything over C2, so okay, let's not get into a why. You know, should I multiply my matrices like this as well? Yeah. Okay. That's true. Yeah. Yeah. So yeah, it should have been a transpose. So by transpose, yeah. Okay. So this is this R1 vector, and this is. I mean, again, this is exactly the spiders from Assoc, the standard basis spiders from Assoc, right? Because this is the sum of all the standard basis vectors, right? I mean, he did it for C2, but for CN it's the same. Okay. Right. So so that's what these look like, right? And I said, okay. I mean, of course, you also have the adjacency matrix is your other intertwiner, right? And somehow by definition, like those three intertwiners must generate everything, right? Because the quantum Roberson group is defined as being like this universal C-star algebra where this U is a magic unitary that commutes with the adjacency matrix, right? So there's a I think it was the green ones, yeah. The standard bases, yeah. The ket 0, ket 1, yeah, exactly, yeah. But not over just C2, right? Over Cn, right? Right. So we also have this adjacency matrix intertwiner, which I guess initially maybe you would just draw it as like some box, right, with an A on it, right? Okay, with a wire on either side. Right? I call these wires. Right? I guess he also called them wires yesterday, right? But turns out the way you should draw it is as an edge, which you have to somehow distinguish from a wire, which in my case, I'll just make it real thick. Okay? So this is a vertex, this is a vertex, and these are wires, and this is an edge. And this is a vertex, and this is a vertex, right? Okay? And now you can compose these things, right? So you can, I mean, in the same way that, I mean, you would do it like in Bob's talk, right? You can kind of, like, if I have, like here, I could have, say, and then here I could have right, and now I can compose those things, right? And then this is, what is this going to look like? Oh, it's going to look like okay. And so what you are getting essentially is, when you're composing these things, is you're getting graphs. But you have graphs where you also have these kind of wire things coming off either side. Good. Yeah. I mean, remember, a wire is just an identity, just the same as Bob's talk. Okay. So somehow, like, you can contract them down. Okay. Okay. So
anything kind of inside the graph always has to be a fat edge, because
if it wasn't, it would just contract down. Exactly, right? Yeah. Okay. And so when you're composing these intertwiners, right, these matrices, right? I mean, in terms of the diagrams, you're kind of just building these graphs. We call them bilabeled graphs because they, I mean, if I want to write down in terms of like not just a picture, right? That I have a graph, and then I need to tell you sort of what's the thing with the first wire on the left, and what's the thing with the second wire on the left, right? So I think of it as sort of like I have some label on the vertices or something. I have some left labels and some right labels, right? Yes. Okay. And actually, this notion of bilabel graph comes already from, like in the graph theory literature, from like there's a book by Logos, and he talks about these things. He's using them for all this graph limit stuff, right? So it's not like a new notion, right? but it turns out to be exactly also what's going on here. You need to, I guess the point is, what are the graphs you can build, right? Because you have these three generators, like these things, right? And then you have certain operations, right? You can do multiplication, which corresponds to this kind of series composition like this. Tensor product corresponds to kind of like a parallel composition where you just, like this is tensor product of A with itself, right? So you're just putting one on top of the other, right? And then, okay, you can also take this like transpose or conjugate transpose, which is, again, it's like reflecting about the vertical axis, right? Yeah, and yeah, that's basically it, I guess. And then you want to know, okay, what can I generate using those operations? Right? Okay, and it turns out what you can generate are exactly sort of planar bilabel graphs, meaning that you can draw it in the plane without any crossings, where you also have that you can't cross the sort of wires hanging off the sides, right? And of course, you need that somehow, like the first wire is on the right is sort of the one that's on the top on the right in the picture, on the very end of the picture, right? So like I can't have like this or something, right? That's not allowed. Okay. All right, so you get that the things you can get are these planar bilabel graphs, and you can get all of the planar bilabel graphs. In fact, you can show, right? And in particular, like a 0, 0 intertwiner is just a planar graph with no labels or anything. Okay, and now you can use this and like this theorem of relating the orbits of the quantum automorphism group with the disjoint union and quantum isomorphism to show that. You know, the generator, I mean, just these three generate all intertwiners, right? These planar bilabel graphs, that's all intertwiners up to linear combination. So if you just take, those give you all the intertwiners as long as you allow linear combinations of those.
Could you tell us exactly what you mean by bilabel graph?
I mean a graph. So a bilabel graph is this thing, call it, right? This is a graph. This is a tuple of vertices. This is a tuple of vertices. That's it, right? And diagrammatically, what this looks like is I draw the graph, right? And then the vertices here are the things that have the wires coming off to the left, right? So I mean, I could have two wires coming off of this, right? So then this would be like the first two things in the first tuple, right? The first two things in the first tuple would be this vertex, right? And on the right tuple, it would be this vertex and then this vertex, right? Okay. So. And of course, you can have some vertices with no labels as well. They don't appear in either of the tuples. And there's no conditions whatsoever on the tuples, right? For a general bilabel graph, right? Now, the ones you can generate using these things, you only get these planar bilabel graphs, which, as I said, means you can draw it in the plane without any crossings, including the wires. If you want to completely rephrase it in terms of graph theory, then you take your picture of your graph, which has the wires coming off, right? And now for all your wires, you turn it into an edge with a vertex at the end, right? And now you put a cycle to those vertices in the sort of obvious order you do, right? And now you put a new vertex that's adjacent to all of those things. And this has to be planar. If you don't like this new vertex, you can say that just this thing has to be planar, but with the cycle you add, it bounds the outside face. Okay. Yeah.
Are the thick edges like contained in the data of the bilabel graph, or is that an additional?
The thick edges here are just the edges of this graph. All the edges are thick edges. The thin things are wires. Those aren't edges at all, right?
Because whenever you have a wire, you can just contract it.
Yeah, somehow like if you had like he was saying before, somehow like if you had a wire like between two vertices of your graph, right? Then you just contract those. Those go away, exactly. Yeah, yeah. So the only wires you have left are the ones hanging off that have no vertices on one end. Exactly, right? So you can't contract those. Yeah.
U and V can intersect in principle, or
sorry?
U and V can intersect, so can
Yeah, of course. Yeah, I mean, That's no problem. This doesn't matter. Right? I mean, this is also still planar even, right? Okay.
Speaking and speaking to it would simply not try to
Sorry, say again? Huh?
Like the second.
Then in the graph you would simply not write H. So we would compose it.
Oh, in terms of the bilevel graph, this is a graph with a single vertex, no edges, right?
Connected with another multiple. Yeah. So we would simply not write H.
The question was, so what happens if you take M and if you compose it, say, with M tensor 1?
With M tensor 1. Ah, yeah. So I mean, yeah. I mean, okay, we can do as many pictures as we want, right? So if I have this M, right, and I compose it with M tensor 1, right? So this is like this, right? Then this is just going to be
Only edges come from A.
yeah, the edges only come from this A, right? That's where the edges come from.
Yeah, try to remember whether they go left or right.
Wires and edges.
Yeah. If you like, you can keep, if you want to, you can keep the wires and just imagine there's an identity matrix in all those wires, right? But I don't think that's for me, that's not the best way of thinking about it. Right?
Loops when you have A.
Like if you can get loops. For instance, if I take, like, I guess the easiest way to get a loop is if I take, like this tensor identity. Actually, identity. I want to draw identity like this, right? And then I take M dagger, I guess. Right? If I do this composition, right, then somehow this merges with this, which merges with this, and this merges with this, which merges with that, right? So both of these, everything becomes a single vertex, but this edge stays, right? So I get like a loop and this, okay?
And then depending if your graph is reflexive or irreflexive, you can simplify that.
Yeah, I mean, if your graph has no loops, then this is, I mean, as a matrix, this is the zero matrix. Right? Okay, I mean, what is this? This is the Schur product of identity in your adjacency matrix, right? So you just get a diagonal matrix with a 1 everywhere there's a loop. If there's no loops, you get 0. All right. Anyways, though, I guess the point of this is that, okay, you can figure out exactly what these intertwiners are up to linear combinations. Oh, I guess I didn't tell you how to kind of, I mean, okay, there's this picture, sure, but like, what's the sort of the correspondence to the matrix, right? Okay, but the correspondence is that you're counting homomorphisms from this kind of bilabeled graph thing to your graph G, right? But you are partitioning your homomorphisms according to the images of your labeled vertices, right? So for any particular, well, let's just take this one for example, right? Well, it's maybe a little complicated for an example, but like, if I look at the intertwiner for this, right, then I'm counting homomorphisms from this path of length 2, right? I will have a matrix. Actually, in this case, the matrix is. Oh, let's get rid of these extra ones, just to make it simpler, right? So I will have this will correspond to an intertwiner, which is like a 1-2 intertwiner. Right? So the rows are indexed by vertices, columns by ordered pairs of vertices, right? And if I look at, say, like the, let's call it V1, comma, V2, V3 entry of the matrix corresponding to this picture, this diagram, right? What it's going to be is, so let's call this vertex, I'll just call this vertex 1, 2, and 3. Okay. What this entry of my intertwiner matrix is going to be is the number of homomorphisms from this path of length 2, such that this vertex number 1 gets mapped to V1, vertex number 2 gets mapped to V2, and vertex number 3 gets mapped to V3. Okay? Right? In this case, it's going to be 0 or 1 because I've told you all the images of all the vertices, right? But in general, maybe I have some other vertex up here that has no wire on it, right? Now I can have more homomorphisms, right? Okay, so it's counting all the homomorphisms from your from the sort of just the graph part of the bilateral graph, right? But you're partitioning those homomorphisms according to the images of the vertices that have wires coming off of them. Okay, and then you're counting the size of all those parts in that partition. Okay, so this V1, V2, V3 entry of the matrix is going to be the number of homomorphisms from this graph, such that this vertex number 1 is mapped to V1, vertex number 2 is mapped to V2, and vertex number 3 is mapped to V3. So if I sum all the entries in the matrix, I just get the total number of homomorphisms. Okay. All right. Okay, and the point is that you can use this to show that G and H are QC isomorphic if and only if this so this is the number of homomorphisms from F to G. So if the number of homomorphisms from any planar graph to G is equal to the same to the number of homomorphisms from that planar graph to H, that's if and only if the graphs are quantum isomorphic. Okay, and this is some sort of analog of this result of Lovaas from 50 years ago. It says that two graphs are isomorphic if and only if this is equal for all graphs. Okay. All right. Well, we were talking about it yesterday, but I guess we don't really understand, like, I mean, you still get all these intertwiners and stuff, but like, I don't know if this, like, what the interpretation is in terms of, like, okay, cool, yeah, I mean, I think me and lots of other people will be interested, so, yeah. Okay, so yeah, you can prove this is kind of like, I think, very nice and surprising theorem that me and Laura proved back in, what was it, 2019 or something? Yeah. Anyways, I mean, we were surprised by it. I think it is surprising. I mean, when you see this definition of quantum isomorphism, you definitely don't think about counting homomorphisms or planar graphs, right?
If you think about counting homomorphism, you definitely don't think about quantum isomorphism.
Yeah, the other way around. You would never prove it the other way around, I don't think. You can't start by counting homomorphisms from planar graphs and get to quantum isomorphism. That would be shocking. So. Well, maybe someone can, but not. I don't think we could.
People in graph theory, they look at, I don't know, counting homomorphisms to some classes of graphs.
Yeah, so this is, if you vary this fam. Yeah. So especially the last few years, they've really started, like, if you take like all graphs in some family, right? Then this is called being homomorphism indistinguishable over that family, right? And there's lots of things, like, so if you say if the family is all graphs of true width at most k. And actually, it relates back to this Y-spheral. There's like a k-dimensional version of this Y-spheral layman, where instead of ordered pairs, you look at k-tuples, right? And so it's saying that two graphs are not distinguished by this k-dimensional Y-spheral layman. And there's more recent paper with the. Oh yeah, of course. If this family is cycles, it's exactly that the graphs are co-spectral. Yeah. Yeah, because. Yeah, okay, so for cycles, it's because when you count homomorphisms of cycles, you're counting the number of closed walks, which is the traces of the powers of the adjacency matrix, and that tells you the eigenvalues, right? If you know the traces of the powers of the adjacency matrix, or of any matrix, then you know all its eigenvalues, right? Okay? If you take trees, or forests, I guess, right, this gives you exactly fractional isomorphism. Okay, this thing I said about the doubly stochastic matrix, which is also the thing with the non-signaling correlations for the isomorphism game. If you take paths and cycles, it's that the graph and the complements are co-spectral. And then there's a recent paper with Peter and Prim, my PhD student Prim, and Tim Seville, where we look at this MPA hierarchy for the isomorphism game. And we showed that for each level of the NP hierarchy, right, this is going to be feasible if and only if the graphs are homomorphic and indistinguishable over some family of like some subclass of planar graphs. And then we show that, okay, if you take kind of the union of all these families, you get all planar graphs, right? And then now you get a new proof of this, right? Because you know this MPA hierarchy converges. Right? So you get a new proof of this result using this MPA. And then you don't need, then I guess maybe it's not good for people in this room, but like you can avoid all the quantum groups. Right? So you don't have to learn anything about quantum groups if you don't want to, right? So it,
Is it easy to, sorry to interrupt, so is it easy to say, to explain which are the family of planar graphs for the kth level of the hierarchy, for example?
no, it's not easy. They're generated, so.
These kind of operations.
Okay, yeah, so you can take, so if you're at the kth level, right, in this case k is 4, so I have k vertices here, right? I guess I should have made, the cycle are thick edges. I'm just going to be lazy. Okay, so I can take any kind of minor of this, meaning I can delete some edges or I can contract some edges, right? So that's one set of generators. Also, instead, I took a perfect matching. Right? I can take any minor of this. So again, I can contract some of those edges or delete some of those edges. Right? So those are all your generators. And what you're allowed to do is this kind of series composition corresponding to multiplication. Or also you can do this kind of like a Schur product, essentially, which is where kind of I take, if I took two of these things, I take the vertex with the first wire on the right from the first graph, and I identify it with the vertex with the first wire on the right from the second graph, and so on for all the wires, right? But I'm only allowed to do that for minors of this bilevel graph, not this one. Okay?
Arbitrary graph was a minor of the.
An arbitrary bilevel graph in the class with this thing, right? And then you can also do the series composition with an arbitrary, like with any of these, or the minors of these, right? And you can take conjugate transpose or whatever, I guess, maybe. And you can rotate them, right? So I can make this go over here and this go over here. Yeah, okay. But yeah, I don't know how to describe it. For k equals 1, it's outer planar graphs with some condition on the wires. But the underlying graph is exactly outer planar graphs. So graphs that are planar, but there's a cycle that has, there's a face boundary that has all the vertices. All right. Laura's going to be upset because I've yet to get to anything.
I would say like planar graphs are like, you want to solve some problem, then trees is the first thing you look at, this is simplest, and then the planar graphs is the most interesting. So it's a natural question, just from purely combinatorial point of view, to ask is homomorphism in the solution. And they would never think of quantum isomorphism, so that's what the connection is super
Yeah, and I
interesting.
think what's really strange is, right, that often things become easy when you look at planar graphs. If you want to determine some property of graph level in planar graphs, this says that determining this equality of homomorphism count is undecided. And for these common like people who look at it, they would never guess that the complexity of this problem would be undecided.
Oh yeah, I remember when we were telling someone about this on the set. They were like, we made them guess what do they think it is, and they were like, oh, is it in B hard or like no harder, like, and they just keep going higher and higher.
So I guess in the paper you also put as a problem which is not for QC but Q, whether there is some sort of.
And there is, but for Q, there is not, you can't do it with Q, because you can show. So if it were, for Q, if there was such a result, it would need to be a superclass of planar graphs, right? Okay. Well, it would have to contain a non-planar graph because it's stronger than QC.
Yeah, I mean, I guess
just asking for different class graphs with exactly this, that's maybe not the, I mean, I'm just
Yeah, you can't do that. Some other characterization. Yeah, no, I don't know. I mean, yeah, maybe if you somehow are counting homomorphisms from infinite graphs, but then I don't know how to do that exactly. That's still open, yeah. But you can't do it with finite graphs with exactly the same thing.
Any hope for QA?
Well, if it's equal to QC for isomorphism, then yeah, sure. And but if it's not, then no, for the same reason. For the same reason.
Because it seems like using QA has to do with the R omega.
Maybe that's infinite graphs. Yeah. Yeah.
Maybe these graphs have to be somehow representations or something.
I don't know.
So, sorry to delay. This F and G, F and H, can they be solved with a classical isomorphism?
Yeah,
For the right side.
in the classical case, you can also do on the other side. Yeah, and it's also equivalent for isomorphism. Yeah. Presumably not here. Almost surely not here, I guess. No, but I would. No, not off the top of my head, but I would guess that.
It sounds so wrong that you can probably run a program and quickly find a pattern.
Yeah, I would guess that I can just take the pair of quantum isomorphic graphs and check some planar graphs and get that that's not true.
Thinking of the Q, because I mean, for Q there is the other hierarchy, but coming from below. Right?
I see what you're saying, but I'm not sure that's sort of the relationship there. I don't know.
It will not be super kind of thing over the place. It will be stuff.
I see. Yeah. No, I don't know. All right. I guess it's 11:30, so maybe I have to stop. But well, I prefer not to. But if everyone else wants me to, I will. So people might want to leave. So. All right. I'll keep going, I guess. All right. So we're going to talk about the connection to linear system games. Okay, we'll start with an example, the canonical example. So this is this Merriman-Perez magic square game. Okay, so the way this is played, usually the classical description is that, okay, I have this 3x3 grid. I'm gonna ask Alice a row, Bob a column, okay? And they were gonna have to tell me an assignment of zeros and ones to the elements in their row, and the elements in Alice's row, and Bob to the elements in his column, in such a way that for Alice, the number of ones is even, right? So the sum mod 2 is 0, right? For Bob, the sum mod 2 is 1, okay? And they have to agree on the intersection, right? And of course, classically, you can't do this perfectly because that would correspond to actually filling out this grid in that way. But then I'd have that all the row sums are 0 mod 2, so the sum of everything is 0 mod 2. But all the column sums are 1 mod 2, so the sum of everything is 1 mod 2. So I can't have that, right? But it turns out quantumly, you can win this game perfectly using. Yeah, you can use. You want me to write down the? Yeah, okay. So actually, the better way of thinking about this is not in terms of 0 and 1s, but in terms of plus and minus 1s, right? So 0 is going to get replaced by 1, and minus 1 is going to get replaced, 1 is going to get replaced by minus 1. So you're just mapping, you're taking, say, b to -1 to the b. Right? I shouldn't use b here. I'll use that later, right? Okay, and then I'm replacing addition with multiplication. Right? So I'm putting plus or minus 1s in here so that the rows multiply to 1 and the columns multiply to -1. Okay? So for instance, I need that like x1, x2, x3 equals 1, but I need x1, x4, x5 equals -1. Right? Okay. And of course, again, classically, you can't do it. It's the same thing as before. I just changed ones to minus, like zeros and ones to plus and minus ones. Okay. But it turns out you can do this quantumly. Essentially, you can satisfy all those relations with matrices, essentially some tensor products of Pauli matrices. If you pick them in the correct way, then you can satisfy all 6 equations. Right? Yeah, just for a tensor product of 2 Paulis for each one of these things. So you can satisfy all those conditions, right? And that also gives you a strategy to the game. Okay. Yeah. So. Right, so I should say that, and then in general, what's happening is I have a linear system that looks like this, everything mod 2, right, over Z2. Okay, and now the game is played, in this case I said Alice gets a row and Bob gets a column, but I could have given both Alice and Bob rows or columns. This game doesn't really change, okay? And in particular, when I can give them both rows and columns, and now it's a synchronous game. Because if I give them the same row, they answer the same thing, right? Because they have to agree on all the variables that are shared, right? And same column, same for the same column. Okay, so if I think I have a general linear system like this, then I'm going to give each of the players one of the equations from the system, right? And they have to assign values only to the variables in that equation, right? But I still want to think about it in this multiplicative way. I mean, I write mx equals b, right? But really, I'm thinking like, oh, I have x1, x3, x6 equals -1, right? Or something like this, right?
Could be different number.
It doesn't have to be 3. It doesn't have to be 3, right? It could be any number, right? Okay. But when they get the constraint, right, they have to assign plus or minus 1s to all the variables in that constraint, right? That satisfies the constraint. And if Alice's constraint has any variables in common with Bob's constraint, they have to agree on all the shared variables. Okay, so they have this kind of consistency condition. Okay. Right. So that's the game, right? And again, classically, of course, you can win it perfectly if and only if there actually is a solution to the system, right? But then in the quantum case, what happens is that, well, in the QC case, I should say, you can win it if and only if you can find some operator solution to the system. So again, now I don't have to make these plus or minus 1. I need to make them they have to square to identity, right? So this is for all my variables, right? And I also need that they satisfy the constraint. So for instance, I'll just do this example, right? If I take well, I guess minus identity, right? Okay. And if it were 1, it would be plus identity. Okay. The other thing you need is that the variables in a given constraint have to all commute, right? Otherwise, like you need to also specify the order. Right? Okay. So you need that xi commutes with xj. Right? If there exists k such that m k I equals 1 equals m k. Right? This is just saying that there's some equation that has both those variables in it. Right? Okay. And I guess maybe if I want to write this out in general, then I should just write out product over I of x I to the m k I equals -1 to the b k times identity. Okay? Right? So this is just a multiplicative form of the kth equation from here. Nothing more than that. Okay? Right? And I can write it like this because of this condition, right? So this is unambiguous. Okay? I guess I also need the Hermitian, right? Yeah. I'll get to the solution group. I'm now talking about only operators, right? Okay, so I also need that they're Hermitian, right? So
I wanted to say, like, for each thing you have a unitary representation of the solution group.
sure.
That's equivalent.
Okay. Right. So these are the conditions I need. So if I can find some operators that satisfy this, then I can get a perfect QC strategy for my game. Okay, and vice versa.
Again, you get the trace, right, from some group.
Yeah, the trace is okay. Well, yeah, the trace is going to come from some group construction, right? And for the Q strategies, you need that you can find a solution with some finite dimensional matrices. Okay, but it's equivalent in that case. Okay.
QA is very similar.
You have to be able to solve these in omega.
Okay, if you want like a rough idea of why this is related to these strategies, so I take this operator, right, for this thing, right? Now it has a plus eigenspace and a minus one eigenspace, right? And somehow the projections onto those eigenspaces, well, they're not the measurements I use because I'm using a measurement for a whole constraint, right? But because of this, right, all those projections for variables in a given constraint commute with each other. So I just take all the possible products of all those projections, right? Okay, some will be 0, right? But they will sum up to identity, okay? And that gives me my projective measurement, and then my outcome will be basically a tuple of plus or minus 1s, right? Because I'll get an outcome which corresponds to, oh, it's the minus one eigenspace for this variable, it's a plus 1 eigenspace for this variable, and so on. And that gives me my solution that I send back. Okay, and yeah.
I mean, these two are the same. We really struggled with that.
Yeah, I mean, you have, okay, there's some work involved, but that's the idea, right? I mean, of course, yeah. And then also, the other way, if I have the strategy, now I have a bunch of projections, right? But the thing is, now I kind of have like, for every constraint, I have a bunch of projections. So to get like, say, the projection onto the one eigenspace for x sub I look at one of the equations that x sub I appears in, and I sum up all the projections where corresponding to a solution where I sent plus 1 for x sub I, right? And that gives me a projection, which I'm going to say is the projection onto the plus 1 eigenspace for x sub I, and similarly for minus 1 eigenspace. The problem is I need to check that these are the same for 2 different constraints that x sub I appear in, right? But you can do that, okay? So
There is like kind of a more general setting that just binary constraint system.
That's true.
That's what was first introduced
that's true.
by Cleveland.
Yeah. Yeah, I should say, yeah, they first look at these binary constraint games where you just have some, you have variables and your constraints are, oh, you want some clause or something satisfied, right? It has to be just some subset of tuples of 0s and 1s that you respond with, right? And then you can consider like a very similar type thing, like Laura said, right, where you need some, I guess you can replace all these constraints with some sort of polynomial, right? A multilinear polynomial.
It's a very nice correspondence with perfect quantum strategies correspond to operators.
Yeah, exactly. Yeah, yeah. That holds in the more general case where it's not a linear system. Right? And that was looked at by Cleve and Mattal originally. And then the linear system, they were first looked at by Cleve, Liu, and Slavstra. Right? And then Slavstra went off and did all this solution groups, well, more stuff with the solution group. Okay, as Josem mentioned, this is related to something called the solution group, which is the group with generators x sub I, right? Where now I kind of, I ignore this because this doesn't make sense in a group, right? Where again, I have that they're all square to the identity in the group, right? If they appear in a constraint together, they have to commute. Now this I have to be careful because there's no minus 1 in a group, right? So what I do is I just make, I replace the minus 1, right, with an element, a new element that I call j. I also don't need this identity here anymore. Right? Okay, a new element which again squares to the identity, and this should commute with everything. So it's a central element of my group. Okay, and so now this defines a group which is called the solution group of the linear system. Okay, so and the theorem is that there's a QC strategy if and only if j is not identity. Because if J is not identity, then you can find some representation where it's not identity. I guess you have to somehow restrict that representation to the place where like J is kind of minus identity or whatever, right? And then you can use that and it gives you your operator solution. Again, very hand wavy, right? But that's the rough idea.
J is again a reflection, right?
J is, yeah, I have that J squared equals identity now in my group, right? And J commutes with everything. I need that J commutes with everything. Yeah, exactly, yeah. So I can restrict to the negative one eigenspace of the image of J without causing any problems, right? Because everything commutes with it.
This is some quotient of the concept. But people look at this in this language, or
I don't know. Okay, but that's the theorem. There's a QC strategy if and only if J is not the identity in the solution group, which I think is a very nice result because, I mean, I think I heard Slofstra sort of point out that like, oh, it's kind of very interesting that like you start with this linear system and you somehow like you associate this group to it. And this is not something that really been done before. I mean, lots of things are known about linear systems, right? They've been studied forever, right? But somehow associating this group to it somehow was something that was never considered, but it sort of turns out to be a very useful thing to do. Okay, right. Okay, so that's the solution group. And what Slofstra then goes on to prove is essentially, I don't know the exact statement of the theorem because it's a little bit more technical, but essentially you can embed any group in the solution group of a linear system in a particular way that allows you to prove a bunch of results. For instance, it allows you to prove that it's undecidable to determine if J is identity or not, which means it's undecidable to determine if you can get a perfect strategy for this linear system game in the QC framework. He also goes on to prove that it's undecidable also to find if there's a perfect Q strategy. Okay? Also, it allows him to separate a bunch of these kind of correlation sets, right? So I guess if you take some group that where J is not the identity, but in every finite dimensional representation, J is the identity, right? Now there's a QC strategy, but no Q strategy. Okay? All right? Okay, but you need this kind of powerful embedding. Well, actually, I think he has now. He has a newer proof that you don't need the full embedding theorem. But originally, he had to prove this kind of embedding theorem for solution groups to do it. And so he separates Q and QC in terms of existence of perfect strategies, even. Right? I guess it wasn't even known if the correlation sets were different.
Yeah, for a long time we were.
Right.
CQA.
Yeah, maybe the correlation sets actually for Q and QC are the same. That was open for a long time, right? And then Slofstra proves that they're not equal. And then he also proves that the correlations set for Q is not closed. So the QA set is different from the Q set, right? So it's separate. And then also, then someone came along and did this using some other stuff that showed that the Q and QS correlations are distinct, I believe, right? I'm pretty sure. Okay. So then we have that Q is different from QS. Which is also different from Q. Did they also show it different from QA? Now I'm not so sure about that one. The QS is different from QA. This is also should be because the closure of Q and QS is the same, right? So if Q is different from QA, then so QS is. No, that doesn't follow. No, it doesn't follow. Okay. Anyways.
D'Angelo found a 4-input, 3-output game that had a perfect QS strategy.
Right, yeah, so they separated Q and QS, but then QS and QA is going to be separated because the Slofstra separated Q and QA perfect strategies for the linear system games, and for that QS equals Q, or for perfect things. Okay. Then the
Also follows from our stuff that we showed that synchronous QS is the same as Q.
synchronous QS is the same as Q, that's right, but then you still need to separate Q from QA for synchronous games.
We've already got Q separated from QA by Slofstra's, and then we showed that's the same as a synchronous game. So
Yeah, but that's what I said. I said Slofstra separated Q and QA, right? And then since by your result that QS and Q are the same for synchronous correlations, then that should do it.
QS from QA.
Yeah, that separates QS, yeah.
And then D'Angelo separated Q and QS.
Yeah. I didn't remember who did the Q and QS, but it's just on the correlation side of things, right? Not a game.
But somehow, at first, like these software results, like they need games that are very, very big.
Yeah.
But like Vern's results,
Yeah. Vern has a much easier proof where that separates Q from QA, right? With only 5 inputs or something, right? Yeah. Very so. Yeah. Yeah. And actually, it was very soon after Software, I think, right? And Software get guys in some very nice journal, right? And then okay. Yeah. Well. Yeah.
It appeared in the journal before the slot.
Oh, okay. There you go. Okay. Right. But then the only thing left, of course, to separate was QA and QC, and then this was recently done in this MIP star equals RE's paper, which is very hugely complicated. But also, I think, uses only synchronous games. Also proves it for synchronous games. Okay. Right. What was I going to say now? I guess I should say something about this hyperlinear stuff. So, as I said, I wanted to say what the definition. What is a hyperlinear group? Right? Yeah. I looked it up. Maybe this is wrong. I just looked in some paper. A group is hyperlinear if it's isomorphic to a subgroup of a suitable family of unitary groups of finite rank with their normalized Hilbert-Schmidt distances. I don't know what that means. But then there's another theorem in that paper. And I guess I took a picture of it because I was too lazy to write it down. It says, it basically seems to be that, it's hyperlinear if for any finite subgroup and for any epsilon greater than 0, you can find some like kind of almost homomorphism to a unitary group, like of n by n matrices, n by n unitaries, where no distinct elements of your finite subgroup don't get mapped too close together. Right? I guess that prevents you from mapping everything to identity, right? Yeah, so I guess it's somehow like every finite subgroup is somehow maybe like somewhat like arbitrarily approximatable, whatever, by a unitary group, I guess is the idea. Okay, so that's what a hyperlinear group is. And the big open question is there a non-hyperlinear group? And I guess this is kind of like the Conness embedding question, but for groups. Right?
Do I get the definition of hyperlinear, the definition of software, and replace the symmetric groups by
Okay. Yes. Now. Okay, so what does this have to do with linear systems? So Slofter, okay, there's some slide. Oh, Mike's not here. Okay, so Mike kind of confirmed this, but there's some slides from Slofter that claim that there exists a non-hyperlinear group if and only if there is a linear system game that has a perfect QC strategy but no perfect QA strategy. Okay, so it's if and only if. All right. And so then, right, yeah, so then the thing I wanted to point out is that there's a connection between the linear system games and isomorphism games. Okay, so we can reduce a linear system game to an isomorphism game, and it's the last thing I'll do, and then I'll let you go to lunch. So if I have a linear system, right, mx equals b, right, what I'm going to do is I'm going to build a graph out of it, right, where the vertices in my graph are like an equation, let's call it equation sub I, and then some solution. Right? Right. So, but just for the variables, yes. No, I'm sorry. Yeah. Right. Okay. So I take. Okay. Actually, maybe I'll just write it as. Okay. So. Okay. Some. Yeah. Right. So the vertices of my graph are going to be just an index of an equation, right? So indexing some row of m. And then a solution just for that equation, meaning an assignment of plus or minus 1 to the variables in that equation, right, that satisfies it. Okay? All right. And then I need to tell you how they're adjacent. Well, they're adjacent to some L, comma, G if they are somehow inconsistent, right? So if f and g inconsistent. Meaning that these equations corresponding to the k and L rows of M, they share some variables, and f and g don't agree on all those variables. Okay, then we put an edge. In particular, that means if L and k are equal, right, and f and g are not equal, I always have an edge, right? So for somehow for a fixed equation, I get this kind of clique in my graph, right? Okay. But if the equations have no variables in common, there will be no edges between any of those vertices. Okay, so this is the graph I build. And so then the theorem is that I'll call it, let's call it g of m comma b. So g of m comma b is qc. Actually, it doesn't matter what I write there. M comma 0. Right. This is if and only if this perfect. QC strategy Okay, so these graphs are quantum isomorphic if and only if there's a perfect quantum strategy for this linear system game. Okay, and this is also true if I replace QC with Q, actually for all the different classes of strategies.
In particular for classical, the same.
Yeah, also yeah, for classical, yeah. And the way, actually you can prove this. Well, one direction you can show just directly in terms of the game. Okay, so suppose I have a winning strategy for my linear system game. Now I'm going to try to use that as a black box to play my isomorphism game for these two graphs. Okay, so I'm going to get as my input for my isomorphism game. Let's say this is an input, the input graph for my isomorphism game. Okay, I get a vertex, which is a constraint and a partial solution. I pretend I'm playing the linear system game using this constraint. I get a solution for that equation. And I just take kind of like the entry-wise product with this thing, and then I output just this first entry is going to be the same, and I output sort of this entry-wise product for the second thing. Okay, so if I get the same vertex, right? That's like then when I'm playing this linear system game, I'm using the same equation, so I get the same partial solution, right? And so when I do this entry-wise product, I get the same thing. So Alice and Bob will be consistent if they get the same vertex, they output the same vertex, right? Also, it's easy to see that, well, if the vertices they get have some variables in common, right? If they disagreed, right, then after doing this entry-wise product thing, right, since the things they're taking entry-wise product with, they come from answer here, they have those things are consistent, right? So I have consistent and then inconsistent. When I take entry-wise product, it stays inconsistent, or vice versa. If it were consistent and consistent, then I stay consistent, right? So it preserves this consistency or inconsistency. So it preserves adjacency. You also have to check that you actually get a vertex over here, but that's because I'm taking an entry-wise product with something which is either equal to 1, both are equal to 1, and so then I take 1 times 1, I get 1, or both are equal to -1, right? And so when I get -1 times -1, which is 1. Okay, so that gives me the strategy. To go back the other way is a little bit harder. If you color the graph, then it's not so hard. If I restrict to saying that, oh, I have to keep the first entry the same, then you can go back the other way very easily. Same thing. Okay? All right. So the point is that because of this theorem of Slofstra is that so if there exists a non-hyperlinear group, then this QA isomorphism is not QC isomorphism. Okay, because if there's a non-hyperlinear group, then there's a linear system that has a QC strategy but no QA strategy, and then there's a paragraph that's QC isomorphic but not QA isomorphic. Okay. All right.
So you said the color
universe is also kind of in this kind of claim by software that it's exactly the same thing.
Yeah, you don't have an if and only if here, not yet anyways. So open question, can you do if and only if? Other open question is, can you go back the other way? Can you reduce the isomorphism game to the linear system game? Okay. Yeah, I guess that would give you if and only if for this other thing, yeah. But in general, it's an interesting question whether you can reduce this isomorphism game to a linear system game. I guess if you can do it, you have to do it in some non-polynomial way because, well, probably, because you probably can't use linear systems to solve graph isomorphism, right? Not expect.
So I still don't understand. I mean, if it's if and only if here, can you just go both ways? So existence of a non-hyperlinear group is the same as existence of perfect QC, that's not QA, it's equivalent to that. And these two things for some linear constraint system game, and then is the same thing as existence of the.
Yeah, but if I just have the, this is not the same. The graphs don't have to come from the linear system reduction. Yeah, that's why I asked, can you go back the other way? Can I take two arbitrary paragraphs, right, and reduce that to a linear system question, right? Yeah.
The linear system game stuff is often generalized for doing things over CP.
Yeah, that's true. Although I think the embedding theorem, he hasn't proved this embedding theorem for ZP. I think that he told me that there's some issues with that. But everything else I think is true.
And you have to prove out the algebra. Is there a way in the ZP case to get a similar graph isomorphism?
Yeah, you should be able to do the same thing. Okay, I should be maybe a little bit careful. I mean, it certainly hasn't been written down. Yeah. But I think it should be fine. Yeah. I should point out that Adina has a very nice theorem about like the algebra for this linear system game versus the algebra for the corresponding isomorphism game. Not that they're isomorphic, but they are related by somehow taking some quotient or something like, or homomorphism or something in both directions, right? Which also proves this like, oh, you have a strategy of one type if and only if you have a strategy of one type in the other thing.
You have a representation that sends j to -1 is the same as going to the group algebra and saying that if you look at the two-sided ideal generated by j plus 1, so you're making j plus 1 equals 0.
Yeah.
Then that group algebra is non-trivial and that's isomorphic. The algebra is a synchronous versions. That's it.
But she also has a result relating this.
Between the solution group and the linear system game. And you're saying between
Also between the.
and the graph game.
Yeah, I think she also has a result relating it to the algebra from the graph game. I thought, but maybe I'm misremembering.
I'm not sure, I haven't seen that.
Well, maybe I could be misremembering, but I thought she did. Anyways, also, if you could pick a slightly different graph here. So you could also make vertices for the variables in the linear system. So 2 vertices for each variable, one corresponding to +1, one corresponding to -1. And now you put edges between constraint vertices and variable vertices if somehow that variable and that constraint is assigned the same as like the corresponding vertex of the variable you're looking at. Yeah. And now if you also sort of add colors to the vertices so that like all the vertices corresponding to a given constraint or a given variable are the same color, then this quantum automorphism group of this vertex colored graph is exactly the dual of the solution group. The homogeneous solution group, I should say, right? And then you can also get rid of those colors if you want to by some lemma of Yosa where you take an arbitrary graph and arbitrary vertex colored graph and you can get rid of the vertex colors by adding some gadgets and have the same quantum automorphism group. Okay.
And that even for there's this paper of my friend and you learn about the cycle of extensions where you have this algebra. So you can show that you can decolor the graph population the whole. And that's using this Weissenberg algorithm you came up with.